Hi, in this video, now we'll look at how to solve non-homogeneous differential equation. So previously what we used the characteristic equation for is to solve for homogeneous ODE. What does it mean to be homogeneous is that the GT term here is 0. But now what happens if this GT term is non-zero? Then we will need some way to find the solution set. And to find this general solution, we first need to understand that any linear combination of two solutions in a non-homogeneous equation, let's say y1 and y2, then the difference between them will be the solution to the homogeneous one. And if y1 and y2 are the fundamental set of solution to this homogeneous equation, then y1 minus y2 will be c1 y1 plus c2 y2. So to prove this, we just let the linear operator of y1 equals to gt, the linear operator of y2 equals to gt, then we subtract it, then this will equal to 0. Then since the linear operator preserves linearity, it is L y1 minus y2 equals to 0. This means that y1 minus y2 is the solution to the homogeneous equation. So this completes the proof. So understanding that now, we take a look at finding the general solution to a non-homogeneous equation. So the proof follows quickly from the previous one. What happens is that if we identify y1 with an arbitrary solution from the of equation 1 and y2 is a specific solution of y, then from equation 3 we obtain that this theta minus y must equals to the solution set of the homogeneous case. So what happens is to find the arbitrary one, the general one, phi, you just need to take this specific and you bring over, so it's the homogeneous case solution plus a specific solution. So if you state it in words, it is saying that you first find the general solution to the homogeneous equation, and then the specific, then this is known as the complementary solution, and then you find some specific solution or particular solution, and then you just take the sum of it. And therefore now it is important, and what we'll be looking at is how to find this particular solution. And the methods will be to use the method of undetermined coefficient. And next time we will then talk about the method of variation of parameter. But for the method of undetermined coefficients, it is usually limited to nice functions such as polynomial, trigonomic, and exponential. So let's first look at the exponential case. So we just consider this non-homogeneous equation. We want to find a particular one that satisfies this. So we see that since exponential replicates through differentiation, to obtain a exponential here, our solution needs to be exponential in nature. So a good start will be to use a constant times this e to t. What we see is that when we when we sub this in and solve, we actually obtain a possible solution for A, which is minus half. So actually, this shows that minus half e to t actually satisfy this non-homogeneous equation and is thus a particular solution. So I hope it's not too hard to see how we choose the particular solution for an exponential case. Basically, you just need to choose the solution that looks like the function t, the t function gt. Then for the sine case is something similar, but let's see. Okay, so let's say we take the same approach. We just take a constant times sine t. We actually obtain this function, and since sine t and cosine t are not multiples of each other, we see that this must be 0 and this must be 0. But then this leads to a contradiction, as this will tell you that a is minus 2 over 5 and this a is 0. So something is wrong here, and what we need to tweak is, because the derivative of a cosine is also sine, so it's possible that here the y can be a cosine. So we just need to add a cosine. So we just need to consider a sine t plus b cosine t. And then this will allow us to find that will allow us to solve for a and b, because now we have two equations, and this tells us that a is minus 5 over 17 and b is 3 over 17. And this tells us that the particular solution is minus 5 over 17 sine t plus 3 over 17 cosine t. So it's not too difficult in finding the solution for trigonomic functions as well. As for products, what does it mean by products? Products means, let's say you have one exponential and you multiply with a trigonomic. Then we want to find the y that satisfies. Well, it's very simple. So very clearly, we just need to use what we already know. This e will be a e t. This cosine will be b sine t 2t plus c cosine 2t. Then you multiply this and this together. Then you actually obtain this solution. So in that case, we just need to differentiate twice, and then you sub both into this non-homogeneous case and actually see that you're able to solve for a and b. And so you actually obtain this solution in the end. Now, what happens if it's a polynomial? Well, we can start off with a quadratic polynomial, so you just guess that it looks something like this, and we see that you're able to solve for the constants a, b, and c. This tells us that the particular solution will just be this quadratic polynomial. And if gt is a polynomial with degree n, then the particular solution will somewhat be a polynomial of degree n as well, because this will be some degree n, and then this will be degree n minus 1, and this will be degree n minus 2. And suppose now that gt is the sum of two terms, g1 and g2. Then the solutions will be, and y1 is the solution to this g1 and this y2 is the solution to this g2. We can easily prove that by adding y1 and y2 together, it will be a solution to gt. So this holds for any finite sum. So for example, this case where the sum is a gt, so you got exponential plus a trigonomic plus this, then you just need to solve each equation individually and then you add them up together, the particular solution, and it will be the answer. Lastly, we'll just take a look at the last example on handling certain exceptions. So we want to find the particular solution of this, and in the preceding example we just assume that it's ae minus t. What happens is that since the left hand side is 0, there is no choice of a that satisfies this equation. So something is wrong with our particular one. And what we realize is the reason is wrong is because when we solve the homogeneous equation case, our fundamental set of solution is already containing e minus 2t. So what happens is our particular solution is actually a solution to the homogeneous case and thus cannot be a solution to the non-homogeneous case. So in that case, now what we need is to find an alternative. And one way to find that alternative is to take inspiration from what happens in the case when there's equal roots. When there's equal roots case, you take a function of t, multiply with the ERT. Then in this case now, what happens is that we just need to take ET and you multiply by a factor of t. So you multiply by t and then you differentiate and you check again. And in this case now, we actually see that it works. So the particular solution will be minus 2 over 5t e minus t. So let's say this now is TET, and here has a function of ET. Then what you want is, you want to take t squared ET as your particular solution. So for handling exceptions, we see whether our original guess satisfies the homogeneous equation. If it does, then we just need to modify our guess by multiplying it with some degree n t to the power n term with our homogeneous solution. And then this will allow us to figure out what is the particular solution. So to avoid making the wrong guess, we will always like to solve the homogeneous case first. So I've come to the end of this video. I hope you've enjoyed it. Please like, share and subscribe. If you have any questions, leave it in the comment section. I will answer them. And I'll catch you again. Bye.